Okay, so in the last video, what we did was react an alkene, same alkene here, here, and here, with three different sets of reagents. So this was the oxymercuration reaction, this was the acid-catalyzed hydration, and this is the hydroboration. So each of these reagents gave you separate and distinguishable alcohols, and they were distinguishable by the regiochemistry of the resulting product. So the hydroxy group was added in 1, 2, 3 different positions. All right, so now moving on. The next video that we're going to do, we're going to include two new reactions. And so the first reaction that we're going to do is going to be a short and sweet reaction where we do what's called an epoxide formation. So we're going to start off with our alkene, and at the end of the day, we're going to form our epoxide. So this is an epoxide. It's basically a three-membered ring with an oxygen inside of the ring. So this is your epoxide, and that's pretty much it. The only other thing you'll have to know is the reagent to give this epoxide, and the reagent that we normally use is actually, it goes by an abbreviated name, and the abbreviated name is MCPBA. MCPBA. And that name stands for metachloroperoxybenzoic acid. Do you have to know what that actually stands for? No, you don't actually have to know it. But if you want to know what it stands for, the structure of the MCPBA, this is what the MCPBA looks like. So again, metachloro is this chloro is what we'll find out later. We don't have to worry about the naming so much, but it is meta to this whole group. Peroxy right here is right here, benzoic acid. So this is the benzoic acid part. Again, you don't have to be able to draw this, you don't have to be able to give the full name, as long as you know that the MCPBA reagent will take the alkene and convert it to an epoxide. That's all that really is required. So, and this is a very cookie cutter, very easy reaction to learn, because there's really no exceptions like there were exceptions for, you know, the acid catalyzed hydration. We really don't have to worry about Markov-Nikov or anti-Markov-Nikov. The oxygen gets attached to both of the original carbons that made up the alkene, so it's kind of useless to utilize a mark or an anti-mark definition. So anyway, that's pretty much it for the epoxide formation, short and sweet. Okay, so the next reaction that we're going to talk about, I'm going to combine them both in this one video. So hydrogenation is going to be another kind of cookie cutter reaction where there's not going to be that many exceptions, or actually any exceptions really, at the very beginning. And we're now going to take our alkene and we're going to react it with a new set of reagents. So the set of reagents that we're going to play around with are H2 and palladium on carbon. So H2 is a gas, so we're going to have H2 gas. The way you normally do this reaction is that you just take a flask and you just have like a little bubbler with a balloon on the other side, and you just literally bubble H2 gas into the liquid that you use for this reaction. And the PD-C is what it's telling you is that part of the reagent is actually a combination both of carbon soot or dust and some palladium. So palladium is actually the fun part, the expensive part, and you actually don't need very much of this to actually make the reaction go. So you only need a catalytic amount of the palladium to make the reaction proceed. So really what people do is, to make this reaction easier to handle, because you don't need very much, you can mix it with the carbon soot, and then you can measure out the amount that you need much easier, versus having to measure out like minuscule amounts of the palladium. So anyway, the reagent is usually it's given as this combination of palladium and carbon. So anyway, at the end of the day, what we're going to get is this alkene. We're going to convert the alkene. This is carbon 1 and this is carbon 2. We're going to convert that alkene to an alkane. And in this case, what we've done is, if you think about the number of hydrogens on this carbon 2, we've got one hydrogen here, and we've got two hydrogens right here on carbon 1. And at the end of the day, what we really have is 2 hydrogens on carbon 2, and 1, 2, 3 hydrogens on. So what's really happening here, and this is kind of like the epoxide reaction, where you really don't have to worry so much about the mechanism, about what's in regards to what's happening. But if you're curious, what we can do is we can at least identify what goes where. So if we have our hydrogen gas is, you know, looks something like that. We have a singular covalent bond between the two atoms. And what happens at the end of the day is that the palladium that you add allows us to split the hydrogen into its component parts, and both of the hydrogen atoms gets added to different parts of the molecule. So one of the purple hydrogens gets added to carbon 2, and the other purple hydrogen gets added to carbon 1.